Greetings to all. This is Mohammad Junaid from Data Science stream B section. So today I am here to give a presentation on applications of delta to star transformation. So let's get started with the presentation. Yeah. So our topic is applications of delta to star transformation. So let's go for the introduction part. Yeah. Before going to the applications of delta to star transformation, firstly, let's try to understand what is delta star transformation. So here, delta star transformations and star delta transformations allow us to convert impedances connected together in a three-phase configuration from one type of connection to another. And we can now solve simple series, parallel, or bridge type resistive networks using Kirchhoff's circuit laws and mesh circuit analysis or also nodal voltage analysis techniques. But in a balanced three-phase circuit, we can use different mathematical techniques to simplify the analysis of the circuit and thereby reduce the amount of maths involved, which in itself is a good thing. Standard three-phase circuits or networks take on two major forms with names that represent the way in which the resistances are connected. So here, actually a star connected network which has a symbol of the letter Y. So here we have to remember one thing is uh, the star connection is denoted by the letter Y and the delta connected network is denoted by the this symbol delta symbol. Okay, and if a three wire supply or even a three phase load is connected in one type of configuration, it can be easily transformed or changed it into an equivalent configuration of the other type by using either the star delta transformation or delta star transformation process. A resistive network consisting of three impedances can be connected together to form a T or T configuration. It's nothing but when either the star delta transformation or delta star transformation process, a resistive network is formed in the shape of T. Okay, T configuration. But the network can also be redrawn to form a star or Y type network as shown below. Okay, it can be formed in the T shape or Y type network as shown below. Here is an image of that. So here, this is a T connected and equivalent star network. So this is called as a star network. Okay, and this is a T network. Okay, and here. As we have already seen, we can redraw the T-resistor network above to produce an electrically equivalent star or Y-type network. So here, this T network can be redrawn to the star network. Okay, so this is a star shaped. So this can be also be converted to the star network. Okay, yeah. But we can also convert a pi type resistor network into an electrically equivalent delta or delta type network as shown below. So in the above pic, we have seen that a, T network has been converted to the star network, and now in the next picture we will see that a pi network will be converted to the delta network. So here it is a picture of it. Yeah. This is what a pi-shaped network. Okay, pi connected an equivalent delta network. This is a what pi network, which can be converted to the delta network. This is the delta network, which is in delta shape, and this is in a pi shape. Okay, this converted to the delta network. Now, Having now defined exactly what is a star and delta connected network, it is possible to transform the Y into an equivalent delta circuit. So, okay, now it is possible to transform the Y network into an equivalent delta circuit, and also to convert a delta into an equivalent Y circuit. Here equivalent is nothing but the values of the delta are same as in the Y circuit. That's why the equivalent is mentioned over here. The Y into an equivalent delta circuit. Y network is converted into an equivalent delta circuit, and also to convert a delta network into an equivalent Y circuit using the transformation process. Okay, this process allows us to produce a mathematical relationship between the various resistors, giving us a star delta transformation as well as a delta star transformation. Okay, so while transforming from the star delta or delta to star, or we can say Y to delta or delta to Y, we get a mathematical relationship between various resistors, between various resistors. Okay, so here, yeah, these circuit transformations allows us to change the three connected resistances or impedances by their equivalent measured between the terminals 1 to 2, 1 to 3 or 2 to 3 for either a star or delta connected circuit. However, the resulting networks are only equivalent for voltages and currents external to the star or delta networks, as internally the voltage and the current are the different, but each network will consume the same amount of power and have the same power factor to each other. So as I have said you earlier that the equivalent term is mentioned. It means if the some amount of energy or some amount of charge is there in the Y network, when we convert it to the delta, the same charge, the same amount will be transferred to the delta one. So that's why the equivalent term is mentioned. Okay, so both have the same equivalent network. Okay, now here delta star transformation. To convert a delta network to an equivalent star network, we need to derive a transformation formula for equating the various resistors to each other between the various terminals. Consider the circuit below. So here we will be going to see a delta to star transformation in a mathematical representation in this picture. This is a delta to star transformation. This is a delta 1 and this is a star. So here you can see that the same amount of energy or charge, whatever you can say, has been converted, equivalently converted to the star one. Okay. Now for this we have a mathematical representation that is here. Now compare the resistances between terminals 1 and 2. Compare the resistances between terminals 1 and 2. So here the terminals 1 and 2. So now first thing we are going to compare the resistances between the terminals 1 and the terminals 2. Okay, here P plus Q is equals to A. Here see P plus Q. In the star network, P plus Q is equals to A in the delta network. So firstly, what we are choosing? We are choosing our terminals 1 and 2. We are calculating these two. And in the star network, it is P and Q. So P plus Q is equals to A. P plus Q from the star network, which is equals to A from the delta network. Okay. And here in parallel with B plus C. So these are in the parallel B plus C. Okay. As mentioned here with in parallel with B plus C. Now, P plus Q is equals to A into B plus C divided by A plus B plus C. So, see here, P plus Q is equals to A we have taken, and we have divided by the sum of all this A plus B plus C. Okay, A plus B plus C, and this is mentioned as the equation 1. And here, resistance between the terminals 2 and 3. Resistance between the terminals 2 and 3. See, the resistance between terminal 2 and 3. Okay, in 2 and 3, Q plus R is equals to C. See here, Q plus R, we have equated to this C. Got it? Yeah. In parallel with A plus B. This is parallel with A plus B. This is parallel with A plus B. These both are parallel, right? A and B are parallel. So we have taken that here parallel with A plus B. So here Q plus R is equal to C into A plus B divided by whole divided by A plus B plus C. Same as the equation 1, mark it as equation 2. Okay. Firstly, we have taken this terminals 1 and 2, then 2 and 3. We have taken P plus Q is equals to A. Then we have taken this both as a parallel networks. Okay. Then we have taken terminals 2 and 3, Q and R, resistance between Q and R. We have taken Q plus R is equals to C. Then these two both will go as a parallel. Okay. Now resistance between terminals 1 and 3. Between 1 and 3. 1 and 2 over, 2 and 3 over, now 1 and 3. Okay. P plus R is equals to nothing but B. See over, P plus R is equals to B in parallel with A plus C. Here we have taken P plus R is equals to B. Now these both are parallel, A and C. So we have written here A plus C are in parallel. So P plus R is equals to B of A plus C divided by A plus B plus C. This is marked as equation number 3. Okay. Now, this now gives us 3 equations and taking equation 3 from equation 2. Now, minus equation 3 minus equation 2 is equals to P plus R minus Q plus R. Okay. P plus R is equals to, this is the, we have taken this minus Q plus R is nothing but from this equation 2 we have taken. Okay. Now, P minus Q we have, P minus Q we have to do B into A, BA plus BC divided by A plus B plus C. Here also CA plus CB divided by A plus B plus C. This A plus B plus C take common. Sorry, do LCM. We will get A plus B plus C as common. Then BA minus C. Now, then rewriting equation 1 will give us, okay, P plus Q is equals to AB plus AC. So this equation can be written as A into B AB plus A into C AC, okay, divided by A plus B plus C. The same has been written here. P plus Q is equal to AB plus AC divided by A plus B plus C. Now adding together equation 1 and the result above of the equation 3 minus equation 2. Now add equation 1 and the subtraction of equation 3 and the equation 2. Add those both P minus Q plus P plus Q, will be getting this. P is the common here. So P plus P, 2P will get. And here also AB, 2AB, AC minus CA plus CA get cancelled. We will be getting 2P is equals to 2AB divided by A plus B plus C. Okay. Now we move to the next slide here, from which gives us the final equation for resistor P as P is equals to AB divided by A plus B plus C. Okay. Then to summarize a little about the above maths, we can now say that resistor P in a star network can be found as equation 1 plus equation 3 minus equation 2, or equation 1 plus equation 3 minus equation 2. Okay. Now similarly, to find resistor Q in a star network, is equation 2 plus the result of equation 1 minus equation 3, or equation 2 plus equation 1 minus equation 3, and this gives us the transformation of Q as this. Okay, from the above one, same how we got the P, we will be solving this Q also, Q resistor also. So we will be getting this answer, Q is equals to AC divided by A plus B plus C. Now, and again, to find a resistor R in a star network is equation 3 plus the result of equation 2 we have to take minus equation 1 or equation 3 plus equation 2 minus equation 1, and this gives us the transformation of R as R is equals to BC divided by A plus B plus C. So firstly, no need to find all these three resistors. If we find only this P resistor, we can automatically write Q and R resistors also. So when converting a delta network into a star network, the denominators of all the transformation formulas are same, A plus B plus C, and which is the sum of all the delta resistances. Then to convert any delta connected network to an equivalent star network, we can summarize the above transformation equation as this one. Okay, so to know the delta star transformation, we have chosen the mathematical equation as a process. Okay, and by that we have firstly found the P resistor. Then from this P only we have found the Q and the R resistors. So this is a mathematical equation. We can say P is equals to AB by A plus B plus C. Q is equals to AC divided by A plus B plus C. R is equals to BC divided by A plus B plus C. So uh, in these three equations, one common thing is nothing but the denominator A plus B plus C. This is same for all the resistors. Okay. Now, if the three resistors in the delta network are all equal in value, then the resultant resistors in the equivalent star network will be equal to 1/3 the value of the delta resistors. This gives each resistive branch in the star network a value of R star is equals to 1 by 3 into R delta, which is the same as saying R delta divided by 3. Now, delta to start example number 1. Convert the following delta resistive network into an equivalent star network. So here is the delta 1. Delta network is given over here. Now we have to convert this to the star network. Okay. Here 1, 2, 3 terminals are given, and A is equals to 20 amps, C is equals to 80, and B is equals to 30. So from the above equation which we have found already, we have to take firstly AC. Firstly, a Q resistor, we have to take this one. Now AC divided by A plus B plus C. We know what is the value of A. A is nothing but 20. C value is 80. So 20 into 80 divided by the sum of 20 plus 80 plus 30. 130 will get, and the answer is here. So this is the values of the star network connection. Okay, we have delta network over here. This we have to convert to the star network. For that, we use these mathematical equations, or you can say these mathematical formulas, to convert delta to star. Okay. Now, so the above are these are equations are also known as the applications of the delta to star transformation. And apart from this, there is a one of its major application is the application of delta to star network is nothing but it's used to simplify complex resistive electrical circuits. Okay, if we have a complex resistive electrical circuit, it simplifies a complex one, okay, to a lower complex. Okay, it means it is mostly used to simplify complex resistive electrical circuits. Okay. Thank you.